Hello everyone, and welcome back to another episode of Total Organic Chemistry. This video, we'll be learning about redox reactions on substituted benzenes. By the end of this video, the questions that you should be able to answer are how do I perform reduction or oxidation reactions on substituted benzene rings, and how do I use these reactions to convert between ortho paradirectors and metadirectors. If you need some review on any of these topics, please go ahead and subscribe to the channel and take a look at the video at the top of the screen. We'll start by considering a compound that might look difficult to synthesize directly at first glance. And this is called Metabromoaniline. So we have an NH2 group, and when we have an NH2 group on a benzene ring, we call that an aniline. And then we have this bromine on the meta position from that group. If you remember from my video on directing groups in electrophilic aromatic substitutions, these are both ortho paradirectors. And because both of the groups are ortho paradirectors, if we performed an electrophilic aromatic substitution to try to synthesize this compound, we wouldn't expect to see much, if at all, of this meta product. So how are we going to synthesize this? Well, we can take a look at a pair of redox reactions that we can perform on this nitrogen group. The first of these is if we start with nitrobenzene, so remember nitro is that NO2 group, we can reduce this to the NH2 group, the aniline, in a variety of ways. One popular way is to use some metal catalyst, so this could be zinc amalgam, so zinc and mercury, or some powdered iron as well. And if we combine either of these metals with some hydrochloric acid as a source of H+, this will reduce our nitro group to the aniline. We can also use hydrogen gas as a source of those protons, and we'll also have to add in a metal catalyst like palladium or nickel. If we would like to go the other direction, we can start with aniline, and to oxidize this, we can use something called trifluoroperoxylic acid. So this is going to be a pretty strong oxidizer because we have an extra oxygen on that carboxylic acid group. We also have this trifluoromethyl group that's going to be very electron withdrawing. This is going to oxidize the aniline to the nitrobenzene. And again, if you remember, the nitro group is a meta-director. It's very electron withdrawing from the ring, whereas the amino group, the NH2 group, is electron donating or ortho paradirecting. What that means is by using these redox reactions, we can interconvert between ortho paradirectors and meta-directors. And if we think back to that original compound, this means that to synthesize it, we could potentially take nitrobenzene, perform an electrophilic aromatic bromination, so that bromine is going to add meta because nitro is a meta-director. And then we can reduce the nitro group to the amino group to form that meta-bromoaniline product. And this is quite a common occurrence, so we can look at maybe another example, where now we have the bromine still on this ring, and now we have an ethyl group arranged meta to that bromine. Again, these are both ortho paradirectors, so it's not immediately apparent how we would synthesize this. We're going to use a similar strategy to the one we just discussed. So if we consider this compound, where we now have an acyl group on that benzene ring, we have the two carbons, but now we have a carbon-oxygen double bond on that benzylic position. We can again reduce this using similar conditions. We can use zinc amalgam and hydrochloric acid, as well as those catalytic hydrogenation conditions, so that's hydrogen gas with a palladium catalyst. And like I said, this will reduce the carbonyl group all the way down to the alkyl group. So this benzylic position is very reactive, and we end up with just ethylbenzene as the product. Just like before, we can go the opposite direction, so starting with ethylbenzene. We can actually expose this to the Jones oxidation conditions. Remember, that's using some dichromate salt, so like sodium dichromate, with aqueous sulfuric acid. And this will oxidize the alkyl group to the carbonyl group here. Now this is very helpful because now we can start with the acyl substituted benzene, which remember is electron withdrawing, so it is a meta-director. we could perform an electrophilic aromatic bromination, just like before, to get that bromine on the meta position, and then reduce that carbonyl group to the alkyl group to form our bromoethylbenzene. Let's look at another reason why this redox pair is so important. If we start with just benzene without any substituents, and let's say we want to add this propyl group onto the benzene ring using a Friedelcrafts alkylation. Well, we could use our alkyl halide, so that'll be propyl chloride in this case. And remember, we need a Lewis acid catalyst, so we could use aluminum trichloride. So if you remember, this will perform a substitution onto the ring, so we will have our benzene ring. However, we're going to get a rearrangement in this reaction, so we will actually end up with isopropylbenzene instead of N-propylbenzene. So because that secondary carbocation is more stable than the primary carbocation, we're not going to see a lot of the N-propylbenzene product. So a common way to circumvent this is by using a Friedelcrafts acylation instead. So instead of using propyl chloride, we can use the acyl chloride equivalent, so this is called propanoyl chloride, again with this Lewis acid mediator. And remember that Friedelcrafts acylations do not experience the same rearrangements that the alkylations do, so we will end up with no rearrangements here, but now we have this carbonyl group on the benzylic position. Well, like we just discussed, if we want to reduce that, we could use zinc amalgam and some hydrochloric acid, and this will reduce the carbonyl group down to the alkyl group, giving us the product that we wanted in the first place, N-propylbenzene. So this is a really great synthetic strategy to avoid those rearrangements in Friedelcrafts reactions. Now let's look at another oxidation of substituted benzenes. Let's say we're starting with this N-propylbenzene again. And if we use an even stronger set of oxidizing conditions, so this will be potassium permanganate with some sodium hydroxide and really heating up this reaction, followed by an aqueous acidic workup, so I can just write H3O+. This will not only oxidize the benzylic position, like our Jones oxidation conditions earlier, it will actually cleave this alkyl group all the way to the carboxylic acid. So these are incredibly strong conditions, and as long as you have some sort of alkyl group on this benzene, it will become completely oxidized to this benzoic acid product. Another starting material we could use is this diol. So we have two OH groups here, one is on the benzylic position, and one is further removed on this alkyl chain. Now, if I used the Jones oxidation conditions like I described earlier, so remember that's sodium dichromate or potassium dichromate with sulfuric acid and water, this will produce exactly what we would expect from our knowledge of reactions of alcohols. It will oxidize both of these alcohols, so we will get the ketone on the benzylic position because that's a secondary alcohol. And remember, Jones oxidations, when reacting with primary alcohols, will oxidize to the carboxylic acid. So we will obtain this overoxidized product here. However, we can use a much milder oxidizing agent. This is going to be manganese dioxide, and maybe acetone as a solvent. And this will only oxidize the benzylic alcohol, while the alcohol on the alkyl group is untouched. So this is a really useful set of conditions. Manganese dioxide in acetone will oxidize selectively benzylic and allylic alcohols, so alcohols that are adjacent to some double bond or conjugated system. One final reaction I'd like to consider is starting with this benzylic ether. So this is ethyl benzyl ether. And if we want to cleave this ether, we can again use some hydrogenolysis conditions, so using hydrogen gas and a palladium on carbon catalyst. And this will give us toluene as one of our products, and ethanol as the other organic product. And again, this is a super useful synthetic strategy because it allows us to use these phenylmethyl ethers as protecting groups in organic synthesis. So whereas normal ethers, for example between two alkyl groups, are not cleaved with these hydrogenolysis conditions, we can easily cleave this ether when it is on the benzylic position. So again, that makes this phenylmethyl ether a good protecting group that we can introduce to a compound and then remove later on in the synthesis. I hope this video helped you understand some of the reduction and oxidation processes that occur in substituted benzenes. If you like this video, please go ahead and like and subscribe to the channel. Follow me on social media and my website, and if you're willing and able, consider donating to my Patreon page, which helps me continue creating all of this content for all of you. Thanks for watching.